That's true. That was the one adjustment I had to make, was just like carrying around my garbage for like half the day until I found something
Back in, back out.
found something to do with it. So.
And then we do find trash cans like this cubicle for tiny things. How you doing?
How you doing? Good to see you here. Yeah. Yeah. My wife's doing fine. As much as I should. Not sure Miami is running well next week. Season item? I don't really do much. I'm talking to a couple of guys around town too. They're just kind of
So it's my privilege to introduce our cataract speaker, Yuri McKee. He did his residency at LSU and his cornea fellowship at Emory. Was previously with the Price Vision Group. Now he's local to here at East Valley Ophthalmology in Mesa, working with Warren Hill, who's probably a familiar name to all of us. He's a frequent speaker for AAO and ASCRS, so we're fortunate to have him here with us. The first hour will be a lecture on a paradigm for the surgical correction of presbyopia. I think it'll be eye-opening for all of us that do premium IOLs. So this one we can be more interactive. We have the microphone down here if you want to ask some questions as they come up, and then we'll also have another one I can bring around in case F is needed. So, Dr. McKee.
Well, thank you all. Good morning. Thank you for having me here. It was a long drive, 8 miles away to my house, so saved on airfare and hotel room. It's great. So every slide or two, maybe we should stop and ask questions on this talk, because you need to bring your big brain for this stuff. It's talking a lot about mathematics and a lot of terms. What do these terms mean? I was giving this talk at various universities, and the number of blank stares I got about what does this term even mean. And when your marketing rep shows up with their bundt cakes and their Starbucks, and they tell you how great the lens is, they have no idea what they're talking about. They just don't. They were never trained in this. They don't understand math. They don't understand optics. And I want you to understand, at least speak the language of optics and lenses. And so we might be going back a ways here. And if I'm talking down to you, just tell me to amp it up, and I'll amp it up a little bit. And if I'm over your head, just raise your hand and ask some questions, and we'll bring everybody on board. But there's a lot to talk about here. We could go for a whole hour on this topic, so I'll try to go nice and slow and make sure everyone's with us. The first thing that I want to talk about is simply the anatomical considerations of treating presbyopia. I mean, what are we trying to do here? We're trying to restore youthful vision, full range of vision, hopefully without glasses. And right now, the technology requires some type of diffractive multifocal light splitting, light sharing, and all that as we'll go into today, reduces contrast sensitivity. Well, what about eyes that have a big problem with contrast sensitivity in the first place, like macular degeneration or terrible retinal pathology, or glaucoma, or ERMs? What about up in the cornea with keratoconus or irregular astigmatism or Fuchs dystrophy, right? Just let me encourage you, don't even try to be a hero, because you're going to go the wrong way in these cases, okay? We're trying to maximize contrast sensitivity in this system, and these are systems that inherently cannot maximize it at the point of either the cornea or the retina or the optic nerve. And so in general, I tell people with these disorders, I show them a little model of a multifocal lens, and I say, you're not a candidate. You're just not. Trust me on this. I'm saving you a lot of time and effort and money and headache, and it's just not going to work well for you, and you're never going to be a kid again. You're never going to have youthful vision again. And what we're trying to do is restore and maintain the best vision we can for you with or without glasses. Of course, I'm going to get you the best lens, but we're not going to get you a full range of glasses-free vision. And I show them pictures like this right in the clinic in the computer so they understand why that, your cataract's important, and clearing the visual axis is important, but what's more important is making sure you don't go blind, okay? And it's also more important that I don't put you in a worse place than you are now. So keep all that in mind, and I think that's pretty obvious, and don't let the promise of amazing outcomes or money or any of those other things block your vision to seeing these disorders. I'm always looking for them. Everyone's going to get a specular. Everyone's going to get a macular OCT. Everyone's going to get a picture of the back of the eye that I can stare at as long as I want without them blinking and squinting away. Everyone's going to get a topography. Every cataract patient is going to get all these things on their initial visit with me. If I can't bill for it because there's not a diagnosis there, I don't care. Let it slide away. If there is a diagnosis that supports the billing, then I'll bill for that test. But I'm not going to find out that I missed something stupid when I had those tests sitting right there and it cost me nothing to get those tests done to make sure I knew every detail about that patient's eye. Now, let's get into the meat of this. Let's get into the fun stuff. Let's talk about modular transfer function. Let's look at defocus curves, higher order aberrations, and dysphotopsia. These are the things that are multifocal killers. These are the things that people don't understand why that multifocal is not working when everything else looks normal. I get a lot of referrals for unhappy patients for one reason or another, and most of their surgery went perfectly fine. And I tell them that. Your surgery looks like it was done by a professional. The problem is this particular lens doesn't seem to be working well with your eye, and now we got to go digging and find out why. So let's talk about MTF, or modular transfer function. Just a show of hands, without reading my slide, who could comfortably tell me what MTF is? Okay, good. I'm in the right spot. We're talking about the right thing, because this is important, okay? The human eye, its entire function is to be a contrast sensitivity detector. That's it, okay? That's the simplest way we can put it. And so how would we mathematically define contrast sensitivity, and how would that relate to the human eye? Well, modular transfer function means that if you look at a series of black and white bars, they're changing, or they're modulating, right? They're going from black to white and back again. And so basically it's a measure of contrast, right? Difference between light and dark. Now, transfer just means that if you look at the bottom of the slide where it says object contrast and it shows a slide and image contrast, we're transferring that contrast through a system, in this case an intraocular lens, but it's really the entire optical system. It's the cornea and the lens. And then the contrast is not quite as good as it was when we started. You get a little bit of blur between the lines. They're not so clearly delineated, right? I don't care which lens it is. I don't care if it's your 20 diopter examination lens made of crown glass. No lens is perfect. Every lens has some reflection off the surface. It has some total internal reflection that traps light inside the lens. It has aberrations in the glass so that the light doesn't bend perfectly. You're going to lose some contrast every time you go through even the best lens in the world. And so a function is just basically a graph, right? It's x versus y. So if we ask, what happens to object contrast as it goes through the lens and then gives us an image? That's MTF. It's modulation transfer function. What happens to the contrast sensitivity, and how well is it preserved through the lens. So there's a couple of different definitions here, like you see spatial frequency as lines per millimeter. So if you're working on a lab bench in an optics lab, you're going to talk about lines per millimeter. You see there the little thing on the right-hand side, it says 5 lines in a millimeter, okay? And so that's a cycle. Every black and white bar, that's a cycle. But human eyes don't really think in terms of millimeters. They think about degrees, right? Field of vision. And so a cycle, or one-line pair, per degree is how you might see things talked about when you're talking about a human eye. So if you see someone talking about lines per millimeter about their particular intraocular lens they're trying to sell you, they're talking about their lab bench things. And cycles per degree is more about how it works in the human eye. And people try to use them interchangeably, but they're a little bit different. But you really need to understand MTF. And so when you look at MTF, they're going to give you a curve. And you're going to see modulation transfer function versus spatial frequency. So you know what happened here was somebody had a lens on a lab bench. And all those different colors are different wavelengths. Now, there's a tricky one right here. You get the big 3 companies, right? B&L, Alcon, and Johnson & Johnson. Each one of them has decided to use a different standard in terms of how they measure lenses. The only one that does it right is J&J. That doesn't mean I don't like the other companies, but J&J is the only one that does it right. You need to have a standard aperture that the light goes through, and you need to have white light when you measure it through these lenses. Well, J&J does that. B&L and Alcon use green light. Why? Because it's less affected by higher order aberrations, so they can make their data look better by changing the wavelength of their light. They also can do a little bit better on their MTF if they reduce the effect of higher order aberrations. So they're cheating. As long as you know they're cheating, I guess it's okay. All right, just call them out on it. Hey, why are you using green wavelength to check your lights? I don't look through night vision goggles for a living anymore. I used to when I was in the Air Force. I don't anymore, okay? So my world is not all through a green filter. So keep these things in mind and ask them what standard they use to test the lens, or better yet, just know what their baseline standard is, and then you're going to understand that yours looks better than the other guy because you're cheating, you're using a smaller aperture and you're using a different wavelength. The standard aperture is 6 millimeters. No company uses that because the smaller the aperture you have, the better your visual quality. And white light is the standard, and only J&J does that. So keep that in mind. And then also keep in mind, are you telling me what happens in the lab, or are you telling me what happens in a human eye, right? Lines per millimeter or cycles per degree. Now, we're going to come back to this, but I want to make a point in this slide. 30 cycles per degree is 1 degree of arc, which is 20/20 Snellen vision, okay? That'll be on the test. Just make a note to yourself. 30 cycles per degree, okay? Now, if you have 20/10, you can see 60 cycles per degree. And you can see in I took that from the light field lab down there. They're showing the difference between if you're looking at constant cycles or you're looking at basically more lines per millimeter through a projector there, okay? So the one where we're looking at cycles, that's more in tune with human vision, and the one we're looking at lines per millimeter is more in tune with checking something on a lab bench. But if you want to look at a single number that looks across all spatial frequencies, then you'll see something called the MTF-A. That's basically the area under the curve of an MTF curve, okay? And if we spend a couple of seconds more looking at this MTF curve, and just look at the black line on the top there, for simplicity, you see that when you're not really trying to tell a very intense spatial frequency, your MTF is 1. What this means is you have one big black square and one big white square. Okay, that's a low spatial frequency, right? All you can tell is half the screen's black, half the screen's white. You don't have to have good vision to know that. That's the lowest spatial frequency, so your MTF is very high. As you get smaller and smaller bars of black and white, it's going to eventually blur to gray. And as it does that, your MTF number is going down. So MTF is basically between 0 and 1. Okay, and that's just basically your basic. It's at 0% or it's 100%. So a 0.5 MTF, in just general terms, it's not exactly the correct mathematical way to say it, but I had 50% preservation of spatial frequency at that particular spatial frequency with that particular wavelength. Okay, so you should know that. Now, how does this relate to your daily practice? Your typical monofocal IOL. Somebody shout out an MTF number. It's going to be between 0 and 1. point what? What do you think your typical ZC Boo? The ZC Boo is the standard lens. The J&J ZC Boo is the standard lens against which all other lenses are compared in non-inferiority in almost every clinical study. So if the ZC Boo, what do you think the MTF is of the ZC Boo with white light? I got a 0.4. It's like the price is right. Because anybody else? 0.4 is a number that you're going to see a lot in lenses. The ZC Boo is 0.7, and so is the Invista. Okay, so I think of 0.7 as your standard MTF. That's your gold standard right there. People with monofocal lenses who don't have any other pathology in their eye, who are properly corrected with their spectacles, they tell you their vision is good, yes? Yeah, nice and crisp, Technicolor. Okay, well, an MTF of 0.7 seems to work pretty good then, right? So that's the standard. And when you start getting below that, then that's when people are going to start having trouble. Now, a lot of times what you're going to see when you look at the DFU is the directions for use. It's in every box of every medical device you'll ever use, especially intraocular lenses, right? That little piece of paper that you unfold and it turns into a meter square, and you throw it away every time. How many people have actually pulled out a DFU out of a lens and looked at it? Well, how do you know what you're using? You're going based on what people like me say. I might be right, I might be wrong. Or you're going based on what the rep told you, and they don't know anything about what they're talking about. Trust me, they don't. Because I've talked to all of them, and none of them, they don't hold it against them. They're just kids who went and got a marketing degree, okay? They're just trying to feed their family too. But they don't know anything about this stuff. But you typically are going to see something like an MTF versus defocus. Well, this makes sense. If we defocus something, what we're really doing is reducing the contrast sensitivity of that object. There's really no such thing as blur. We call it blur. But actually, if you defocus something, all you've done is reduce contrast sensitivity. And we describe that as blur. But mathematically, blur doesn't exist. Only reduction in contrast sensitivity exists. So if you look at the zero in the defocus curve, you see MTF is the highest in a monofocal lens. And it's about 0.75 right there, right? This is a theoretical lens, okay? The 0.7 is where they kind of top out at. And then if you defocus that light blue line, minus 1.5 all the way up to minus 3, what that represents is basically someone bringing the object closer to them, right? Because the error is now minus. And the MTF drops to nearly zero. They can't tell how many lines per millimeter or how many cycles per degree there is when looking at that. And when you compare that to your standard bifocal, trifocal EDOF lens, look at how low the MTF is in perfect focus at distance. 0.4, okay? So that's typically what you see with a multifocal lens is an MTF of around 0.3 to 0.4 with no refractive error at plano. So only 30 to 40, maybe 50% of contrast is preserved through that lens in the human eye. The first time I started to understand this, that was a huge eye-opener to me. Why can people have multifocal lenses put in their eye and tell you that they're happy? The answer is, especially in Phoenix or in Vegas, an excess of contrast sensitivity. We all wear sunglasses and stand in the shade around here. We have way too much contrast in our environment here. The sun is so bright. Ask any person you've put a multifocal lens in their eye, can you read the menu in a dimly lit restaurant? Have you ever met someone who could do it? No, because there's a paucity of contrast sensitivity in the environment, and then you've reduced contrast sensitivity in their eye because what did you do? You traded contrast sensitivity for depth of focus. You must do it. Mathematically, it's the only way to do it. You must trade contrast sensitivity for depth of focus when you have a diffractive optic. There's no other way around it. So the question becomes now, as you sit with your patients, how much contrast sensitivity are you willing to give up to improve depth of field without glasses? In other words, how much do you hate glasses versus how much do you need high contrast vision? So I call people good candidates for multifocal lenses surfer hippies, right? Everything's cool all the time. Nothing bothers them. I'm never going to read, the fine print in a legal contract. I surf all day. I smoke dope all day. Cool, man. Then you don't want to wear glasses neither, so we'll give you a multifocal, right? But what if your job is an aerospace engineer looking at micrometers? If your contrast sensitivity is low, a plane might crash. Maybe we're not going to do that, okay? And I explain that to people in these kind of extreme and kind of, funny terms, like, oh, yeah, surfer hippies and, aerospace engineers. But it does make a difference, because once in a while you do meet an aerospace engineer. My son's one, so he's never getting a multifocal. So this is, Warren and I don't just share an office, we share a desk, so I just get to leech off his knowledge constantly, just osmotic learning of all his knowledge. And one of the things he loves to say is depth of field is purchased in the currency of contrast sensitivity. Please remember this, nothing is free. You always have to balance the equation in math and physics. And you don't get free contrast sensitivity when you're adding in depth of field. You just don't. Okay, the next thing I want to talk about, let me stop for a minute, because I'm kind of talking fast because we have only 50-some slides to get through in this hour. Dr. Lee has a microphone, and there's a microphone here. Does anyone have or you can shout it out. Does anyone have a question about modular transfer function? And do you understand it now? Did it make sense before I talked there? Did I make it make sense? Good. There's a question back there. Shout it out. Well, that's a good question. What about the measurement for the natural lens, right? And so can we take a natural lens out of the eye, put it in the bench, and measure it? Well, no. So we don't have the lines per millimeter function, right? But we can project images into the eye. It goes through the cornea, and then it goes through the lens, and then it hits the retina, and then it has to bounce back out and go through the same objects. So they have to pass twice, right? And then we can measure it, right? So there's no direct measurement. It's just like when, does anyone have an eye trace? It tells you what's going on in the lens. How does it know? It just subtracts what's going on in the cornea from the actual autorefraction, which goes through the eye twice to give you a refraction, right? So we don't know. But we think in a pediatric lens it could be as high as 0.8 or 0.9. And in the average lens of a 30-year-old, it's probably 0.7. And as you get a cataract, of course, it's going to vary greatly, but it could drop precipitously. But that's what we think. But without a direct measurement on a lab bench, who could know? Remember, MTF is primarily measurements on lab benches of how does this lens perform before it ever comes to your eye. But that's at least where we can start. Okay? Other questions, MTF?
On the previous chart that you had, it looked like the extended depth of focus lens and the multifocal lens were kind of at the same 0.3 to 0.4 initially, but then as you increase defocus, the extended depth of focus doesn't increase as dramatically as the other ones. What's that like in real life?
Yeah, it's a good question. She's asking why do we see the EDOF lens perform better across a variety of things. You'll notice certain peaks there, and the EDOF lens doesn't reach the peak at -3, for example. This particular graph here is kind of theoretical. It's showing you in general. Don't take this as what the MTF is. Each lens has its own MTF curve, which we'll look at. But generally speaking, you kind of smooth out the curve with EDOF lenses, but you get individual peaks with multifocals. So you see that the multifocal does better up close than EDOF does, right? But over intermediate, and this is kind of the traditional one as well, and the new lenses that are coming out kind of break this paradigm. So there's nothing specific about an individual lens with this. It's just kind of showing you that trifocals, EDOFs, bifocals, they have different peaks, different curves, different area under the curve, and different ways that they slow down. But it's not specific to any lens. I think it's a good question. We're going to come back to it when we look at specific lenses. Okay, we're going to talk about logmar. So before I talk about logmar, let's talk about what logmar means. It means a logarithmic function. And everyone's face just glazed over, right? Any math majors here? Or anyone who passed high school math? Either one, I'll take it. Who can tell me what a logarithmic function is? Okay, I'm going to try my best. I'm not a mathematician. I'm really bad at math. Frank's from Vegas. Okay, the sphere, 516 feet diameter sphere in Vegas. Really cool. Like you've all seen pictures if you haven't been there, right? That gigantic sphere, and they're doing all sorts of ads on it. And a lot of times in the morning, if you're doing the walk of shame or if you wake up early, the sphere looks like the sun. They have it glowing bright yellow, and there's a little smiley face, and it's supposed to be the sun. Okay. If the sphere is the sun, where is the Earth, and how big is the Earth? The Earth would be the size of like an an exercise ball about 4 feet. And it would be in Henderson, Nevada, which is 10.5 miles away. Okay? So relative size and position of the Earth to the sun, that's how far away it would be if the sphere was the sun. Okay? You guys have probably seen examples of that. Well, what if the Earth's a tennis ball? And like, oh my God, the sun's way over there, right? And so if I asked you to graph that out, size of planets versus distance, and I want you to graph it out without breaking the graph and saying, oh, these little squiggly lines mean that there was a break in the action and then we went way down the road here, right? You'd need paper that's miles long to graph this out. So if I asked you to graph out for me the relative sizes and distances between retinal ganglion cells and astronomical units, which is one astronomical unit is the distance from the sun to the Earth. And I want all that in one graph on one piece of paper without breaking the lines or anything. How do you put really, really tiny things and unimaginably big things into the same graph? What if I wanted you to actually talk about the size of the known universe versus the size of subatomic particles in the same graph? Everything properly proportioned out without having a piece of paper as big as the universe. Well, you'd use logarithmic function. That's what you do. So a logarithm is simply a power of 10. Does anyone remember seeing the movie? It's a short film called Powers of 10 from the late 70s. I remember seeing it in the National Air and Space Museum. And you might have seen it. You can look this up on YouTube. It's worth looking up. It's got the funny, weird soundtrack, and it's got the stupid 1970s graphics. But what it does, it starts with a couple laying in the park next to the lakes, Michigan and Chicago. And they start off going, these people are sitting on a blanket that's 1 meter square. And they start zooming out. And before you know it, they're halfway across the known universe after 40 powers of 10 in meters. So 10 to the 40th meters will get you halfway across the universe. And then they zoom all the way back in, and then they start going into the guy's hand and into a white blood cell, into the nucleus, and down to the DNA, and down to the molecules, and then atoms, and then quarks. And then they're 10 to the 40th minus 10 to the minus 40th power. So from 10 to the minus 40th to 10 to the plus 40th, each individual gradation there being an equal distant power of 10, you can go from the subatomic particles in atoms to the distance across the known universe in one graph on one 8.5 by 12 piece of paper. And so a power of 10 is a logarithmic unit. Now, if you want the mathematical definition, logarithmic units are the inverse of exponents. I can glaze over. But basically what we're saying is, to what power of 10 would I need to raise 10 to get a certain number? What if I wanted to raise 10 to 1,000? Right? That's 2, or 10,000, that's 3. You're just adding zeros, right? Now, why does that work well in science? Well, one thing it does is it makes graphs that go all over the place and they're too big, small, compact, and linear. So suddenly we can predict things with great accuracy, and it's not perfectly linear, but it might be a curve, but it's a very predictable curve. So logarithmic functions graph really well, and they take really big differences between things and make them something you can now manage and understand. So log mar is the logarithmic function of the minimum angle of resolution. We already talked about this. What's the minimum angle of resolution of the human eye? It's 1 arc degree, right? And 1 arc degree is how many cycles per degree? 30, which is equal to 2020 Snellen, right? But Snellen is actually feet over feet, right? It's 20 feet at 20 feet. You could see what you should see at 20 feet at 20 feet. And so the logmar is angle resolution, but logarithmic function, in any case, no matter if you're measuring pH or if you're measuring the Richter scale for earthquakes or any other reason we use logarithmic functions on a daily basis, has no units associated with it because it's an exponent, it's not the actual number. It's the exponent to raise 10 to the power you need to get to that number. So when we take the log of the minimum angular resolution, there's a couple of things that really matter. Number one, it refers to an ETDRS chart. early treatment of diabetic retinopathy study. They said, we've got to find a way to objectively measure vision, not just, oh, it's 2040 and 2020, and there's a gestalt there. No. It's every line on an ETDRS chart has 5 letters. I don't care if it's 2200 or if it's 2020 or even better. There's 5 letters, and they all have equal size, equal bars, equal distance between the letters, no matter which line you're on, or within each line, okay? So you can say this person saw 10 letters on the ETDRS chart, and you know that they saw the first 2 lines, and Snellen would be around 2060, but the logarithmic function of that is 0.9. Or sorry, 2160, right? And so if you start at 2020, that logmar vision is 0. That is the starting point, that is the baseline. 0 means 2020 logmar. And then if you went to 2200, remember 2200 best corrected in your best eye, that's legal blindness, right? We don't care about less than 2200. Only retina people care about that, okay? We don't care if you're less than 2200, you're beyond our help. But between 2020 and 2200, how many powers of 10 is there? 1. So if we start at 0 and go to 2200, we've gone from 2020 to 2200 through 0 logmar and 1 logmar. And then every 10th of a log unit between 2020 and 2200 gets its own line. So now we have a very linear way of thinking about vision where every line has 5 letters of the same size, shape, and arc degrees. And we can just say, yeah, if I want to go 1/10 of a unit away of a power of order of magnitude, that's how I'm going to do it with logmar. And the reason we do this is it's the only way to objectively describe vision in studies and actually put it into graphs. Now, we never talk about this to patients this way, but if you want to understand the lenses you're using, you have to understand logmar. Questions on that? Because it's kind of important, but I know that one slide in 5 minutes isn't going to do it justice.
So, like in a clinical setting, would you ever rely on logmar over Snellen? Would it change any management decisions, or is it pretty much research?
It's research. It's research. But the way it works in a clinical study is you need to pull the DFU out of the lens that you propose to put in that patient if you've never done it, and look at the DFU, and it's going to give you a logmar vision chart. You have to understand what logmar means. And if you don't, how can you understand what the chart means? So the only reason I want to tell you this is I want you to understand what we're talking about when we talk about logmar. And so in the very simplest way, 0 is 2020, and 1 is 2200, and minus numbers are even better. What's twice as good as 2020? 2010, right? And so, logarithmically speaking, that would be 0.2, minus 0.2, right? So when we talk about orders of magnitude, when we talk about powers of 10, that's not twice as good. That's 10 times as good, right? So a twice as good change is not one log unit. 10x per unit, that's 1 log unit. Okay, so 2200 is not twice as bad as 2020. It's 10 times as bad. Does that make sense? So I just want you to understand what logmar is. Go powers of 10. Go watch the video on YouTube. It's actually pretty interesting. Okay, so now the next thing I'm going to show you is logmar versus defocus. Now you have seen these before. This is exactly what industry shows you as a chart so that they can tell you how good their lens is. Because if you look at the monofocal lens there at 0 defocus, then your logmar is pretty close to 0, which is 2020, okay? And how far would you be willing to fall down that logmar chart to say, no, my vision's not worth anything anymore? Personally, what would you accept as a logmar vision for yourself to get by in a day-to-day basis? I'll help you. I'll go back one. Look on the side of the chart. It says logmar 2040-ish maybe. Okay, 0.3, right? So logmar 0.3 is about 2040. You probably wouldn't want to accept less than 2040 to get by on a day-to-day basis. That wouldn't be ideal, but at least you could get by. You could still drive, okay? So if you look at this chart here, when you get past 0.3 in the logmars, you fall down that vertical axis there. You're really not functional after that, okay? And then they're going to defocus things. And the only reason you have hyperopic defocus is if the surgeon made a miss on their mathematics. But then on the minus side, you're saying, hey, how can they do at a near-sighted focal point of -1 to -2? And then they're showing the multifocal lens stays above 0.1 to 0.2, so that's 2025 to 2030, all the way out to -250 to 3. Hey, that's pretty good. So nobody should be expecting 20/20 at their intermediate or near range with a multifocal. The math doesn't add up for it. You're going to trade contrast sensitivity for depth of field. We already said that. But the monofocal lens drops off really quick so that at -1, -150, you're already past 2040 and it's not that functional anymore. That's what this graph means. Does that make sense? Is that helpful that now you know what logmar versus defocus curves mean and how to read them? I hope so. I drove 8 miles for this. Okay, so then what I did for this talk is I started going, you can go onto the webpage down here, this Access Data FDA, for anything. I don't care if it's a hip replacement or anything. And you can say, give me the DFU for this approved device. The FDA said it's approved for use, right? Okay, so here's the Vivity MTF curve versus defocus. This is directly off the DFU. This is from the pivotal phase 3 trial that the FDA used to approve this for implantation into humans. So I'm giving you the data that the industry thought was convincing enough to give to the FDA to get their approval. So if we read this here, now again, we're not looking at logmar, we're changing again, we're going back to MTF on the bench, the modulation transfer function of a Vivity, that's in the dark black, and then they're comparing it to an SN60WF, which is in the light gray, 0.25. They're telling me that 25% of contrast is preserved on the bench in a Vivity. Who wants a Vivity in their eye after you look at this? Who's placed Vivity? Did they want the lens out? The majority of people have an excess of contrast in their lives. They didn't want the lens out. You know what the #1 lens in the last few years that I've exchanged was? Vivity, hands down. You know how many Vivity I put in? 0. They've all come to me asking for it out. So while the vast majority of people who get the Vivity are happy, a large absolute number of people come looking for that thing to get taken out. So I won't put this in people's eyes myself because I see so many want it taken out, and the MTF curve looks atrocious to me. But remember when I asked what's the MTF of a standard monofocal, and somebody over here said 0.4? You're absolutely right when you're talking about the most commonly implanted monofocal lens in the world, the SN60WF. So the SN60WF, I don't know, Alcon's acrylic is not that great. It's 0.4, not 0.7. ZC Boos and Invistas are 0.7. That explains it right there, doesn't it? Yep. Now you know. A quarter of the contrast is preserved. So if you have really, really tightly packed cones and a really smooth cornea and no refractive error, you're not going to need all that contrast. We have way too much. But if there's any problem, or maybe their brain just doesn't think in the same way, they're not going to like this. So the margin for error on a Vivity is essentially 0. You got to nail it all and have the right patient, otherwise they're not going to like it. Or maybe they don't like it, but they don't say anything. You never know until you really query them.
Could you remind us what the DFU stands for again?
Directions for use. Yep. It's a product insert. That's all it is. You will hear it called the SSCD, where it's have it down there, the FDA Summary of Safety and Effectiveness Data, the SSSD. That's what the FDA calls it, but industry calls it a DFU. But if you look for DFU, you're going to get a whole bunch of stuff that DFU means a bunch of other stuff. It was very crass in the Air Force. We'd get in the crew van and we'd drive out to the jets, and we'd say DFU to students as they got out of the jet. You can figure out what that means. Okay. So anyway, the SSAD is what the official name for the DFU is, and they're in every box. You throw them away every time. You can look them up. You don't have to go tear into your stock. You can just look them up online. Go to the FDA website, look for the SSEDs. They got them for every device you want to find. All right, how about the Apthera? Who's placed an Apthera? Yeah, that's kind of cool. It's a pinhole strategy, right? They want you to put it in the non-dominant eye to improve reading ability. And so look at how the range of defocus actually is pretty even on either side here. So they're comparing this to the ZC BOO, where you can see 0.7 to 0.8 MTF there on the lab bench, and the IC8. And by the way, what's the power of the lens, right? Because it makes a difference whether you're at the high and low end or the middle. They're always going to be in the middle, like 23 diopters in the middle of the range. And oh, by the way, they're using green light, cheaters. And we're using this at 50 lines per millimeter on a 3 millimeter aperture. Well, now, they're not cheating on that aperture. The aperture standard is 6, but this actually has a 3 millimeter permanent aperture in it. So, okay, we're fine with that. And you can see, compared to the ZC BOO, that you just have about a diopter to a diopter and a half on either side of plano, plus or minus, where you can preserve some contrast sensitivity. You know, maybe at least 0.4, okay, or 0.3 if you have good lighting. Right? So what happens with the small people in dim lighting? Really bad, right? It's not going to work. So that's an Apthera. Anybody use the lens tech? You know, do you like it? Meh. It's best MTF as at actually -2, not at plano. So here, instead of using the standard defocus curve, they flipped it upside down on us. They put the 0 all the way to the right and the minus to the left. That's the opposite of how the defocus curves are usually done. So that's just to confuse you, okay? And then their MTF curve, they just stopped at top at 0.4 instead of going all the way to 1 because they didn't want to make their curves look like they're on the bottom of the gutter there. Like, no, give me a real MTF curve. A real MTF curve starts at 0 and goes to 1. If you didn't know this, you'd think these lenses are performing fantastically. No, they're at the bottom of the MTF curve. Well, still, if there's an excess of contrast and you can read at -2 to -3 and they peak out there, that's great, but their distance is meh. And yeah, this lens actually got pulled from the European market for a while because of this. So I don't use this. And also it's hydrophilic acrylic, which I think should be taken off the market. It eventually, given enough time, will opacify, it will calcify, and I take these things out all the time. And they scar into the bag, so I can't save the bag, and I have to do a Yamane after a vitrectomy, and I'm getting old and I can't do it anymore. This is one of the most popular multifocal lenses, the Panoptics. Now notice, are we talking about MTF? No, we're talking about MTFA, that's area under the curve, but that's actually data, the MTFA data and the two smaller curves right next to each other. That's not in the DFU. I had to go looking for it. I had to find it from these German people who did it in an obscure journal. Because Alcon didn't want me to look at the MTF and be like, wait a minute, you're telling me that with white light, your MTF from the Panoptics is only 0.35, and with green light, to get a little advantage, it's 0.4, that's it? And this is also not MTF, but MTFA, so area under the curve. So I understand why they didn't want to put that in their DFU. So what did they do instead? They put log contrast sensitivity. Oh, that's cool. Contrast sensitivity, that's what I want to measure. And we already said we like logarithmic values because they're an easy way to look at things mathematically. But here's the problem. If you look at that graph, you can barely tell the difference between a monofocal IOL and a Panoptics in terms of cycles per degree across the log of the contrast sensitivity, right? There's no difference, right? Those curves nearly overlap. Those curves represent a 50% difference in contrast sensitivity because it's logarithmic values. So tiny motions in logarithmic values equal huge changes from across the room to across the universe in the same graph. So a 0.1 log loss of contrast sensitivity is 17% reduction, and a 0.3 is 50% reduction. Okay, so yeah, log contrast sensitivity is a great way to do it, and more industry is using this instead of MTF to talk about how their lenses perform. But you got to understand something. Microscopic changes in log contrast sensitivity are huge deals. So they did this because the graph looked nice, not because it shows good performance of the Panoptics at all. It shows terrible performance of the Panoptics. So take that for what it's worth. I put them in, but take that for what it's worth. Okay, so now this is relatively new. This is the B&L Envy. This is a trifocal lens. And so when you look at this, it's kind of the same thing. This log units of contrast sensitivity to the right, and then logmar versus defocus. The logmar versus defocus on the left, that looks amazing. All right, you're really holding up above 0.2 all the way out to minus 250, then it drops off. Actually, I've heard this. I haven't actually put in any envy. I just used some different ones, but the people who put in envy, I've talked to them like, yeah, it actually works really well. People have a lot of preserved contrast sensitivity. In other words, a lot of good vision. Not as good as distance, but pretty good across intermediate and near. So ignoring things like rings around lights at night, we're just talking about the pure Logmar Snellen acuity across defocus. Envy does pretty good. Trifocals in general do pretty good, but that curve is pretty smooth. So I mean, that is a good one right there. But if you look at the log of contrast sensitivity, so Logmar and contrast sensitivity measured differently, and there's a 50% reduction in contrast sensitivity at 6 cycles per degree. Remember, 30 cycles per degree represents 20/20, but it turns out that that's on the lab bench. But in real life, it actually turns out that most of what we see is between 6 to 18 cycles per degree, and beyond that really isn't useful. So 6 to 12 is the standard, and so that's where they look at. And look at the reduction in contrast sensitivity from their standard MX60E to the envy. It's significant. And the only reason you get away with this is what? There's an excess of contrast sensitivity in our world around us. So yeah, it's a good lens. You get away with it in most situations, but they're never going to read in dim light. And they've got to know that before you put it in their eye. Otherwise, you're explaining it afterward. All right, so what about the Odyssey? I like the Odyssey a lot. That's what I use as a multifocal for many patients. And the surgeon who did all the pivotal work in the studies in the Odyssey flew his wife out from the East Coast and told me, put an Odyssey in her. So I was like, don't I get a say? No, she's getting an Odyssey. And so these people do reasonably well. But here's my issue. The Synergy was this multifocal lens that Bausch & Lomb came out with between the Symphony and the Odyssey, and the Synergy was garbage. I took half the Synergies out that I put in, and I don't even think it's on the market anymore. It was garbage. But the modifications between the Odyssey and the Synergy were so small, the FDA did not require an additional pivotal study to get approved, which means when you pull the DFU out for the Odyssey, it says C Synergy. Okay, J&J, if that's the way you want to play it. That's terrible, but I'm going to tell you the Odyssey is much, much better than this, but this is basically the Synergy. And it looks great in the graphs. But here's the problem. It was very intolerant of any refractive error or any other problem in the eye. So in perfect eyes, Synergy did great. And with any problem of refractive error, you missed a little bit in the calculation, or there was something wrong with that eye, higher order aberrations, Fuchs, PCO, little AMD, little ERM, whatever, Synergy was terrible, absolutely terrible. So now that's the problem, is you get a great lens like the Odyssey and you have to go look at the Synergy DFU and find out this doesn't look good at all. All right, now what about dysphotopsia? And I'm not talking about the dark edge that causes by square edge lenses with the prismatic effect. I'm talking about positive dysphotopsia, which is a feature, not a bug, of all these multifocal lenses. Well, you're like looking at this slide like, man, that's a lot of numbers. I know, but basically, if you just zoom in on one number, like how many people would say, yeah, somewhat or quite a bit, I'm bothered by glare or halos with the Panoptics? 18% and 16%. Ugh, yikes. That's more people than I want to be talking off a ledge after I do cataract surgery on them, right? And so if you look at all these things, these are numbers they have to give you. They're in the pivotal study and they're in the DFU. They're not great. Now, if you're honest with patients and you tell them this, no, anywhere from 15 to 20% of people are going to be bothered by rings around lights at night. How many people are going to be like, well, sign me up, I'm pretty sure I'll be in the other 80%? Like, it's not great odds, right? This is why I don't put many multifocal lenses in. I just tell people what these things are. I say, this is what the studies show. And they go, just count me out. I don't want it. And I don't have to worry about it. So, who understands higher order aberrations? It's more math. I'm sorry to kill you with math. I promise you. Next hour is going to be fun. We're going to have surgical videos and crazy cases, okay? But this is kind of basic stuff. You got to know the definitions, okay? There's a whole bunch of higher order aberrations. Look at all this. This is a pentacam. Look at this big pyramid, this big triangle of higher order aberrations, right? They have Zernike polynomials that go first, second, third order, things like that. Let me just break it down for you real quick. You only need to know 2. That's it. Because if you look at the edges of that pyramid, they're off in the periphery. They don't make that big a difference unless you have massively huge pupils like young people who get LASIK. Then things like tetrafoil and trefoil come into play. But if you're talking about older people with smaller pupils, there's only two that matter. Outside of course, defocus, astigmatism and sphere and cylinder. Of course, those are lower order aberrations. But for higher order aberrations, what do you care about? Two things: spherical aberration and coma. That's it. It's the only two you have to learn. Okay, so basically in spherical aberration, there's a difference in the keratometric power of the cornea between the central and peripheral cornea in the visual axis, which is defined at 6 millimeters. And when you see all these other devices letting you reset the visual axis to 3 or 2 or 1 millimeters, they're just cheating. If you're going to get a 6 millimeter pupil at night, they're going to complain about spherical aberration. All the lights have glowing orbs around them. You're like, well, there's no PCO, there's no ERM, the cornea looks good, what the hell's wrong? And then here's the worst part. Every time you get a topography, you probably have a higher order aberration printout, and then they're not happy, so they send it to me, and they go, what do you mean I got high spherical aberration? Didn't Dr. Jones know this? And I look through the notes that they sent me, I'm like, oh, there it is right there. Yes, they did know it, or they should have, right? It was at least printed out. Okay, so look for this. Look for spherical aberration. The basic limit is about a half a micron of spherical aberration. Okay, so look at this particular case. Do I have a pointer? Okay, look right in the middle. There's four images from the very middle, top of the pyramid to the base, right? There's 4 of them, right? The third one down. That's spherical aberration. 2.132 microns. This is a post either LASIK or RK patient, probably LASIK based on how smooth it is and the fact that there's not very much coma in this Penacam. So they probably had a high myopic LASIK ablation. You should absolutely not put a multifocal lens in someone with 2 microns of cornea. That's just malpractice. It's unforgivable. They're going to do terrible. The limit for a multifocal lens to do well with spherical aberration is a half a micron, 0.5. The typical lens is cornea is about 0.2, 0.3. 0.27 is the minus spherical aberration put into the ZC-BOO because it was supposed to neutralize the spherical aberration that occurs in a natural cornea. Now, there is one lens out there, well, there's a few, but there's one that's known, the Alcon SA6AT lens, and it has positive spherical aberration in it. Lord knows why, but it does. There's only one set of people that should be placed in, and that's people who have radial keratotomy, because they have negative spherical aberration in their cornea. But a couple of years ago, Alcon came into Phoenix and goes, hey, we're giving away this excess lenses we have with positive spherical aberration in it for $25 to $30 a lens to surgical centers. And I had a wave of people coming in after regular cataract surgery with the cheapest lens that surgery center could find, going, my vision is garbage. And nobody could figure it out. I'm like, yeah, that's because you put positive spherical aberration on top of your positive spherical aberration, and it sucks. So I took the lens out, put a ZC-BOO in, or an Invista. They did great. This is why you use negative spherical aberration lenses in post-LASIK patients like the ZC-BOO, because it minimizes, to some degree, the induced spherical aberration of myopic LASIK.
How do you feel about positive spherical aberration on a hyperopic LASIK?
Yeah, that's the one time you might want to think about it, but it turns out that zero SA lenses like an Invista just work better because it's never perfectly round. And so you're never just nailing it. And so just the zero SA and not messing with the system that they're already used to is probably the best way to go. You're really never going to fix all the spherical aberration in a cornea unless you do one thing: hard contact lens. That's it. Okay? Now, coma is simply an imbalance vertically or horizontally of the keratometric power within the visual axis. So spherical aberration, think about an aberration between the center and the periphery in a circular manner, and coma is just one side versus the other, left and right or up and down. Okay? And the limit for a multifocal for coma in my book is 0.3 microns. So if you look here, spherical aberration, go one line below it, and on either side you have horizontal and vertical coma. And it's 0.002, and then 0.04. Well within limits. There's no coma in this cornea. Coma is an absolute multifocal killer. It takes the rings around lights at night and turns them into these big, weird oval or star-shaped rings, and people hate them. So this is really, really important. that your spherical aberration and your coma is within the limits I've given you here if you're thinking about a multifocal lens. So let's take a look at this cornea here. And can you tell, just looking at this Pentacam, what this person has? Do you think they have spherical aberration? Anybody? Their central K is 29. Yeah. What happened to this cornea? Anybody? Also, if you look at the radii ratio back to front, it's in the top middle box there, 96.9%. These are really, really important numbers. I look at this in every patient. First of all, he's extremely flat centrally, right? What can make things go really, really, really flat? RK. RK, right? Even the excimer can't make you this flat. If you try to do hyperopic LASIK or myopic LASIK, you can't get that far off of where you started. But RK can make you go really flat, okay? The radii ratio back to front is also known as the, anyone for bonus points? Gallstrand ratio? You must know the Gallstrand ratio of every person you operate on if you're going to do cataract surgery. You must. Because every IOL formula is based on a Gallstrand ratio on the Pentacam of 83% plus or minus 2%. And if you're outside that, your math isn't going to work. If you have a Gallstrand ratio of 75% and you have no other idea of what happened to that patient, they had myopic LASIK or PRK. If they have a Gallstrand ratio higher than 83, let's say 89 or 87%, they had hyperopic LASIK. And if they're above 90 to 100%, they had they had RK, which is for myopia. So it goes the other direction. So low Gallstrand ratio is myopic LASIK, slightly high is hyperopic LASIK, and way off the charts is RK. And you have to do the appropriate mathematical adjustment for that in your formulas. So you have to know what the Gallstrand ratio is. You have to know what kind of surgery they had. You have to know, with this flat of a central cornea, you see every ring in the anterior sagittal that's 3 millimeters. So we have a massive difference between even the central cornea and the mid-peripheral cornea in keratometric power. This person's going to have massive spherical aberration, microns of spherical aberration. Can't miss it. You'll pay for it later. Okay, so I just need a time check. So we've been going for about an hour then, right? Yeah. So the rest of this is interesting stuff, but I'm not going to kill you with a bunch of stuff. But basically what it talks about is how you preserve contrast sensitivity with aberration. So here you can see if you have what the E looks like with spherical aberration, what it looks like with astigmatism, if you increase spherical aberration, or if you just correct it all. Okay, so you can see that the spherical aberration is going to give you worse blur in that E than even a diopter of astigmatism. If you go from 0.2 to 0.4 in the spherical aberration. That's why you don't put a multifocal in these lenses, okay? And this is coma, and look at those point spread functions of coma and how it looks like a comet, right? And it's really, really annoying to people to have uncorrected coma. Now, these keratoconus patients have multifocal corneas. They learn to look through one part or the other. But you try to put a multifocal in here, and it's going to be a kaleidoscope of disaster, okay? I'm going to skip forward a couple things. Blended vision. Now that I've just poo-pooed on all these other lenses and how they work and how they shouldn't work and all this stuff, I use a lot of blended vision, and I use a lot of light adjustable lens to get blended vision. But to be quite honest with you, this is a 2-hour lecture, and I've given you the first hour of it. So the rest of this was actually written by Warren Hill about blended vision, I've murdered your brains to this point, okay? So I'm going to give you about 2 to 3 minutes, stand up, get a drink of water in the back. I'm going to get a drink of water, ask any questions in the interim, and then we'll just go back in, but now we'll start talking about cool things about surgery, surgical videos, and all the hero stuff, okay? Questions? Please ask. Use the mic.
How do you... Sure.
Oh, is there? There it is. you.
Yeah. How do you feel about like a mix and match strategy with like using in the EDOF and multifocal? Kind of in
Mix and
separate
match, I
eyes?
don't do. I know people have been successful at doing mix and match, but some people they love to do the monocular eye test, and it drives them nuts. So.
So I think we'll
All
get
right, everybody.
started with the
go
second
ahead.
hour. So we've got kind of an assortment of topics. We've got some new IOL technology, the nanophthalmic or the Cincinnati protocol for nanophthalmic eyes, and some interesting cases he has to show us. And for each kind of portion, feel free to and we'll kind of take some questions at the end. But please take advantage and pick his brain while we got his here. We've got him.
Okay, welcome back. Now it's time to have fun. Okay, now we got pictures and videos. You're going to stay awake and no more math. Okay, sorry about all that, but I hope it helped. Okay, do we have an accommodating IOL? This is it, right? This is the holy grail. As a matter of fact, the study was called the Chalice study, or the Chalice. Okay, and so I am the chief science officer for JLC Ophthalmics. I do own stock in that company. I cannot sell you that stock, and I cannot sell you this lens. Okay, it's not FDA approved. So, but this is the lens that we've come up with, and there's a couple different competing designs, and I hope they all come through, because the more the merrier, and doesn't matter, we're all going to get rich. But the road to the accommodating IOL looks like Tombstone, right? Like all these billions of dollars and all these different designs. So we had this Tetraflex, we had the crystal lens. These were all designed on a monofocal lens flexing at some hinge based on capsular flex. It was a bad idea. It was never going to work. It was never going to happen, and it never did, okay? You cannot rely on capsular forces moving to move your lens. It will never happen. Then they came up with a Synchrony. This was like 2007, 2010. It sold to one of the big players for about $400 million, but it was a disaster. So they were saying, well, if we move two lenses within the eye together, we'll get accommodation with a spring haptic. What are they betting on here? That the capsule never opacifies or scars, and that the capsule can induce forces to flex this lens. All that happened is that the capsule scarred and it flattened the lens down to 0, and then they got PCO, they needed a YAG, and then it squirted into the vitreous cavity. So if you heard about this about 10, 15 years ago and suddenly you didn't hear anything more about it, it's because people were doing vitrectomies for Synchronies, okay? And I think it was at what was now J&J, I think it was AMO or Advanced Medical Optics that bought it, and you're embarrassed when you flush $400 million down the toilet. So Fluid Vision, Alcon bought this one, also called Power Vision. So the idea here is to squeeze these oil-filled reservoirs by what? Squeezing the capsule. Can't do it. It's not how it works. And then you'd increase the power of the central element by squeezing those peripheral reservoirs. Doesn't work. Capsule scars down, flattens everything out, done, doesn't work. And then we had Juvene, and Juvene was kind of a hot topic between like 2016 to 2020. And a couple really good things to learn about Juvene. First of all, you put the blue thing, you'd put that in first, and it kind of held the whole bag open. And then you put the optic in second. And then, again, the bag is supposed to flex it or squeeze it, and then that would kind of squeeze. See, if you look really close to the distance in the intermediate near picture there, that the anterior curvature was slightly increased in that accommodating lens. So you have a power lens in the back and accommodating lens in the front, and then the blue thing was supposed to squeeze it. Didn't hear too much about Juvene recently, and so one of a couple things happens. And you get a lot of buzz about something, then it goes away. Either it failed and it died, or it ran out of funding, or they're about to get approved. And they go real quiet so the FDA doesn't think that they're messing with anything. I think the Juvene was good for about a diopter and a half of maybe accommodation. That's not really better than what we get already with non-diffractive EDOF, even like an Aspire, which is technically a monofocal, but someone just asked about the PRC, which is coming out soon, that just got FDA approved. And they're doing better without the dysphotopsias already, so why would you need a big in-the-bag accommodating lens? So my gut feeling on Juvene is we're not going to see it be a player in the final accommodating lens market long-term. So then another recent one here, Atia Vision. They've been at this for about 15 years, I believe. So then you got the shape-changing accommodating posterior optic. That's a little bit different. Most people went for the anterior optic, just like the natural lens does. And then you can exchange the front optic, which is the power optic. And so if you miss, you just you leave the lens in place, but pop that little one out during surgery and then put a new one in there. I'm not sure exactly where they're at or how much accommodation they're getting. They're claiming really, really good visual results, but part of being called an accommodating lens that the FDA is going to require is that you actually show the physical accommodation. And that's really hard to do. That's been one of our biggest challenges, is actually finding a way to show physical accommodation in the eye. Because if I take a young kid and try to show it, it's really hard to do. So if I can't show it in the natural system, how do I show it in these lenses? And so here's how a TIA works. That anterior one is just the focusing element, and the posterior one, once again, has fluid reservoirs that push fluid in and out. And I'm sorry, I just don't think this is going to work, okay? Why? Because the capsule just scars down. It just does. And once the capsule scars down, the capsule doesn't flex, it's not going to push fluid anywhere. Now, this one's interesting. This is the Opera, and this is driven actually by ciliary body engagement in the sulcus. And so they're doing well. They actually had a funny looking lens because you could see this weird lens within a lens in the eye because the index refraction was different between the lens and the oil that it's filled with. They fixed that. So now that's gone. So now it just looks like a clear lens in the eye. They're actually showing some nice results of about 3, maybe 4 diopters of accommodation. The problem is, do you like things in the sulcus? Like, I don't. But they're not seeing any UGG syndrome. They're having good results. So this is promising. This truly is promising. And it may be one that makes it to market. ACO lens is basically 2 lenses. You see they look like prisms, and if they move back and forth, they increase or decrease the power of the lens. This sliding lens things, nah, it's not working. It's not going to work. Okay, it's just not how accommodation works. Okay, so I just showed you a bunch that some of them are kind of working, maybe going to make it. A bunch are not going to make it or have not made it. But here's some important questions to ask before you start designing a lens. How much accommodation is necessary for a shape-changing lens? Well, let's think about a kid. If you cycloplegic kid, what do you get in their refraction? It's always hyperopic, right? Always +1, +2, right? So the first diopter or 2 of a kid, they're just accommodating over the hyperopia that lives in their eye, and they're fine-tuning their vision to 20/20 with that, which is great. And if you know any good LASIK surgeons, what do they do to 20 or 22-year-olds when they do LASIK? They leave them a +1 on purpose, right? They just accommodate over that. Oh, and you're a hero. You hit 0 every time. And you just make them presbyopic a year or 2 early. Okay, but they forgot who did their surgery by that time. All right. But what you need for an accommodating lens is twice what you need for near. And this has been shown in kids, okay? So basically, you need at least 6 diopters of accommodation to be a true accommodating lens. And really more like 7. Because if you leave people +1 hyperopic, so you don't care about their ELP or you don't care about a little bit of refractiveness in the lens, so that's your first diopter of accommodation. And then you need about 3 diopters of accommodation to read comfortably. But think about if you go to the gym and you're lifting weights, right? And I tell you, well, I want you to lift this weight about halfway up, and I just want you to hold it there. Whatever your max lift is not what you're going to hold it there, right? You'd probably, if you could curl 50 pounds, you could probably hold 25 for a time. You couldn't hold 50 for a time, right? So really, you need twice. You need to hold half your accommodation in reserve to read comfortably. You cannot max accommodate and read. You'll give yourself a headache. And this has been well documented in the pediatric literature. So the answer is 7. You need 7 diopters of accommodation to be a true accommodating lens and restore youthful vision. 3 isn't going to cut it, because if you maximally accommodate those 3 diopters, you're going to get a headache. And if you only half accommodate those 3 diopters, you don't have near vision, you have intermediate vision. And this just goes over what I just said. And these are the references for that of why you need to hold 50% of your accommodation in reserve for sustained near focus. Okay, so aren't you glad we did the first talk, talking about logmar and defocus curves first? Because now we're looking at this. We're saying, okay, if we take a 10-year-old with a natural lens, what's their vision over a range of defocus? It is a curve, but you see the curve is drawn through a series of dots, right? So the dots are actually the actual data. So yep, they can still do pretty good with a +1 hyperopic blur, and they certainly can do good through -1, -2, even -3 of blur. But then when you get beyond 4 or 5, man, you're really stressing the system to accommodate hard, and they're 10-year-olds, so they're going to give up. So they start to drop off a little bit. But this is the ideal. This is what we want to reproduce in an accommodating lens. Now, how does this happen? This is very, very important. First of all, how does a little kid accommodate? What happens, let's think about a bubble of air in fluid. It wants to be a sphere, right? And if you try to squeeze that bubble through different forces, that bubble squirts around in different areas and tries to find an area where it can be a sphere. even if it means going deeper into the fluid. So bubbles will go against their buoyancy because of the surface tension to be a sphere. Well, your lens works the same way. What if you have a kid that comes in and they have Weill-Marchesani syndrome? They're short, right? They're kind of squat. They're seriously myopic, and their AC is really deep, and they've just got loose zonules, completely slack zonules all over the place. Their lens becomes a sphere with no other forces acting on the lens. If you lysed all the zonules in a child, their lens would simply go from a lenticular shape to a sphere, which increases its power, right? So accommodation happens all by itself with no input. It's the core basic idea of the lens wants to be a sphere. So really, we don't accommodate when we're kids, we disaccommodate. We pull on the zonules and it flattens the lens and it defocuses to distance instead of up close. Now, if you think about the ciliary body, it's simply a circle of muscles, just like the iris sphincter, it's a sphincter. And if the ciliary body contracts, it makes the sphincter smaller, and the zonules lax, and then the lens, the anterior curvature of the lens bulges forward, increasing power of the lens, and you can bring your focal point closer. So accommodation requires smaller ciliary body diameter across its circle of sphincter to lax the zonules to allow the lens to do its own thing, become more powerful. And then the intraocular pressure pushing against the ciliary body, when it relaxes, stretches the zonules on tension, which flattens the lens and gives you distance vision. So it's kind of counterintuitive. The ciliary body, when it acts, does not pull zonules, it slacks them. So the gradient elastic index of the capsule of the lens causes the lens to go into accommodation because it's stiffer than the soft lenticular fibers in the lens in a child. But as our lens ages and it gets stiffer inside the lens than the capsule is, the capsule can no longer pull the lens into a spherical accommodated state. When I say spherical, what I mean is about 100 microns of flex of the anterior capsule. That's it, okay? The other thing that's interesting about accommodation is that zonules at the equator are quite scarce. They don't really live there. Zonules live in the anterior and posterior capsule, and primarily the anterior. And the anterior zonules are really what's there to accommodate, and the posterior is really what's there to hold the lens in place. So selective zonular force in the anterior capsule is important. And then the last thing that's important about these biomechanical considerations is this. I've used an extreme example of the lens turning into a sphere like microspherus phakia. That's not really what's happening here. What happens is you have a really flat surface in the front of the lens, and then it gets just a little steeper, and that has a huge amount of power change on it. So if you had a really steep anterior lens and you made it steeper, it wouldn't even be a one-to-one change. But if you have a flat lens and you get it slightly steeper, you get a massive change in its power. So these are some things I talked about, the accommodated versus disaccommodated lens. And accommodated is just what it wants to be if you leave it alone, and disaccommodated is what you pull it into. And that's exactly those three things I just talked about. That's what this lens was made for, okay? So if we look at this cross section here, we see these little, we call them actuators. They look like little blocky haptics. They insert onto the anterior capsule of this lens. The posterior element is an IOL. It doesn't flex. And you can put any power you want in there, and you can put astigmatism correction there, whatever you want. The anterior element does not have any power to it other than the fact that it has curvature with a silicone oil in it. And by changing the diameter of this lens by 118 microns, you get 7 diopters of power change in the center of the lens with no rings and no dysphotopsia. So here it is in kind of the side showing those things where basically the accommodating part is the anterior part, the posterior part is the power part. We've inserted the actuators or the haptics into the anterior capsule. And if you just change going from the equator to the capsule 500 microns ahead, you get 5 extra diopters of dioptric change of that lens when you're pulling on it. So it's huge. We can go anywhere from 6 to 34 diopters. As I said, we can put toricity into it because that's just all on the back side, that posterior element of the lens there. And that's just like any other lens that we can just mold it to whatever we want. So this is showing on a lab bench the dioptric power of the lens versus micronewtons of power. So how do we know that the eye can apply this pressure? It's been well shown through many studies that the eye maintains ciliary body tension throughout life, even at 80, 90 years old. And it turns out that this micronewtons of up to 80 is exactly what the human ciliary body can affect. And so when we apply tension to the lens and focus it for distance by disaccommodating it up to 70 or 80 micronewtons, which is well within the known power of an 80 or 90-year-old ciliary body, we can go from 28 diopters down to 21 diopters of power measured on the lab bench. And if we relax the tension across those haptics and the lens becomes more spherical, back up to 28 diopters. And you can squeeze it back and forth and measure this on a bench and watch the power change real smooth. So there's the little puller. Adrian Glasser in the UK developed this little puller, and it can measure right down to the 0.01 Newton or 1 gram, and it just turns out to be identical to what the ciliary body can provide. And so you can see where they stretched and released, what the power of the lens was through every time. And they got those little squares back there, it looks like graph paper, and based on the size of that square and the distance from the lens, you know exactly what dioptric power is being applied to the lens. It's very simple and very ingenious with this little stretcher. This was theoretical MTF. About, when it says 80%, it's 0.8. So the lens was, for the accommodating lenses were 0.8, that then they drop down to 0.3 or 0.4 if they're accommodating. And if you look over here at the graph of our MTF, the MTF of this lens is 70 at baseline and 90 when we're accommodating it. That's crazy. That's better than any lens we've ever seen. So we put this in a primate at the University of Wisconsin, watched it for 15 months, and you can't ask the monkey to read, but he stopped wearing his reading glasses during the study. No, we'd give them atropine and pilocarpine, and then we'd measure the power of the eye, and we could change the refractive power of the eye by 7 diopters. So we did it all on the bench, we did it all in ZMAX modeling, we did it in a monkey, and everything was lining up perfectly. So we put it in humans in 2022, and same thing. It all lined up perfectly. It wasn't hard to do at all. We didn't have injectors back then. We have injectors now. It fits in the bag. You do it just like regular cataract surgery. The one thing is those little blocky arms, those haptics, they're hard to stuff into the capsule. It's like putting a cat in a pillowcase. But once you get them in there, they don't come out, okay? And there's the OCT. You can see how beautiful it looks in the eye. So it's about 1.4 millimeters front to back. Your typical, monofocal lens is 0.5 to 0.6 millimeters. So this is 2 to 3 times thicker, but it still is way thinner than a human lens of about 4 to 5 millimeters. So a lot of times you see a narrow angle and you want to do cataract surgery to open that angle. You think you're buying 4 millimeters, here you're buying 3.5. But look at the angle in this OCT, it's wide open. So it still solves narrow angle. It won't cause angle closure. So here's some of the very, very first average 10 patients on 6-month follow-up. And you could see that they could very easily get to -1, -2. But it turned out all the lenses in this study were handmade and slightly underfilled. So this is what happens when we don't make them perfect, and they still accommodate. The new lenses that we have are made in a very, very complex mechanical structure that measures to the microliter how much oil goes in them, and their accommodation is even better than this. But this is like one of our star patients. Look at his defocus curve versus his vision, and compare it to the 10-year-old child. That's a 70-year-old man having the defocus curve of a 10-year-old child. It's phenomenal. And this is, the more that the capsule scars, the better it works, because the capsule's scarring into the actuators, which pull on the lens. So the capsule's not squeezing anything, it just scars in and makes a solid connection. There is sound to this, but if you don't speak Spanish, it doesn't matter. That's John Vukic there with his coffee, and he's trying to see what the hell line are you trying to show him. That's the fellow down in El Salvador. He's reading 2020 uncorrected day 1. There's Kevin Waltz, okay? And then we're like, okay, you just read 2020 uncorrected day 1. Can you read this? And he's like, sure I can. And he pulls it even closer than the study calls for it to be because he's using angular magnification on top of accommodation. And we're like, no, don't hold it that close. Push it back out to where it's supposed to be. He's like, no, it's clear if I pull it closer. And then he's like reading the tiny print on medicine bottles and all this stuff. Like, oh, now you're just showing off. Okay. But I mean, this is day one in a 70-year-old down in El Salvador. So amazing, amazing stuff. All uncorrected. So here's where we're at in this journey. 2019, this was an idea on a napkin. All that mathematics, ZMAX modeling, optical bench testing was done in 2020, right in the middle of COVID. It won the winning pitch at ASCRS in 2021, and it got some money to go forward, and it did the primate trial. We did the first in human trial in 2022, and then we had to wait, right? Well, what does it look like 3 or 4 years later? Safety. Basically, first in human trials are safety trials, okay? And then we are now into our phase 2, starting in just a few weeks, and then definitive U.S. clinical trial probably next year. So, cool stuff. Any questions on how we're working on accommodating IOL? Oh, great question. Incision size. I don't know if I can tell you right now. It's going to be 3 or less. Let me put it that way. Yeah, through the injector. The last couple of weeks, I've been staying late nights in my surgery center, validating the injector. So I've taken human rims that are not suitable for transplant, and I've been taking calipers, and I've been doing different incisions, and what can we easily get through, and we're going to be 3 or less. Well, we haven't had to explant any. So, we've done explantations in models, which are pretty close. It's not hard. You hook a 30 gauge through the front and you aspirate the oil. And it gets all the oil out really quick because the oil sticks to itself. And then you just pull it out, cut it in half, take it out. So we've perfected the technique in models, and it's easy to do. The one question you might think about is, wait a minute, doesn't silicone oil and silicone lens cause an emulsion? Not if you change the chemistry, and not if you know how to do it. So we have an oil and a polymer that are both silicone-based that do not cause emulsions with each other. They stay crystal clear. And it gives an MTF of better than any acrylic we've ever seen.
Just out of curiosity, a little off subject, but what's the cost from paper napkin to right now at this phase of developing that lens?
Well, I can't talk about the specifics of the finances of that company, but I'll tell you that to take something from a napkin to the IDE study but not get through the IDE study in phase 3 is 30 to 50 million. And then to get through the IDE study, double that. And then to get production going and a sales team and everything like that, throw another 10, 20, 30 million into it. So probably 100 to 200 million if everything goes perfect and you are running lean and fast. But, you know, like these companies out there have spent 200, 300, 400, 500 million getting to places that are far less than where we're at. We have a core team of people who are really motivated, who are very open to the idea that we're going to fail at any day. And my job when I was in the Air Force was to find weaknesses in systems before somebody crashed jets. And I was really good at it. And so that they hired me to do that. And the founder of the company hates it every time I get on the call. Because he's like, we're so close, guys. We're making so much progress. I'm like, let me tell you how it's all going to fall apart. But I'm doing that because let's solve it before it falls apart, right? And so, well, he hates me. He loves me at the same time.
Have you noticed any issues with changes of the capsule over time? Is it becoming more fibrotic?
Well, we do polish it, but it does do the standard thing that you see as standard lens. It's not phimosis, because as you keep the capsule open, the Juvene showed that they don't get much PCO or phimosis. So it's when the two leaflets come together that they really go crazy and get a lot of phimosis there. If you keep them apart, they don't scar much. But in this case, scarring is our friend. We want it to scar into the haptic so it transmits the force of the zonules into the flexible optic. It looks pretty normal like any other cataract, any other lens in an eye that's not having phimosis. And we had 1 or 2 cases of PCO, and we yagged it, and it was no problem. Yeah. So there's actually a little peripheral edge in the posterior optic that's a little bit more posterior than the actual optic itself. So the optic's off the posterior capsule by about 200 microns. So.
You said that you aspirate, if you need to remove it, you aspirate with a 30 gauge needle. Say that you have an optometrist doing the YAG, they put the lens. Are you concerned with that?
No, because the posterior element's as thick as a regular IOL. So you're not going to yag through that posterior element. All right, cool stuff. On to the next thing. I call this the Cincinnati Protocol for Nanophthalmic Eyes. And it's really more of a cautionary tale. Mike Snyder, Cincinnati Eye Institute, amazing surgeon, does all sorts of crazy stuff. So I talked to him a lot, and he came up with some rules for working on short eyes. So nanophthalmos is defined as bilateral axial length of 20 millimeters or less. And you're going to come across these people, and they should scare you, okay? Things can go wrong so fast, so bad, you can lose the eye, and you were just in your regular surgery day not paying attention, and all of a sudden you got a blind eye or something like that. So this should really scare you. They have very high corneal curvature. They have a very high lens to eye volume, so the lens just looks massive inside their small eye, which makes their angles narrow. They typically have high hyperopia. Anyone with hyperopia, especially high hyperopia, should really make the hairs in the back of your neck stand up. You get your spidey senses tingling when you see these things. They have very thick scleras, which is very dangerous because it can occlude the vortex veins. And then they just tend to have a deep set eye because it's physically smaller, so it's back in the orbit a bit, and that which causes ptosis. And because of their massive refractive errors through their whole life and the ptosis, they tend to have amblyopia. So, the concerns when you go inside these eyes, number one, uveal effusion. That can cause the eye to collapse in a heartbeat. Acute angle closure, because their zonules and their capsule are very lax and they flip back and forth very easily. They have aqueous misdirection commonly, which can lead to malignant glaucoma and angle closure. And they're also more prone to iritis and CME. So like I said, when you see this case, just refer it out, okay? There's no good things that can come from it, all right? So here's a 75-year-old lady who came to me, very dense cataracts, been looking for cataract surgery for about 5 years and cannot find a single surgeon willing to touch her. She's a +8. Oh, she got some goutte, just for the fun of it. Her axial length was 18 in each eye. A normal corneal thickness, lens thickness, 5.59. Like normally it's like 4 or 5, right? She's almost 5.5, approaching 6 in her lens thickness with a super short eye. And look at her Ks, 48, 47 instead of 44. She's not had any refractive surgery. 11.3, so a little bit smaller white to white, a little bit smaller eye, right? And so, foolishly, I agreed to do her surgery. These are some pre-op testing. This is just an optos. Look at how terrible the optos is great at getting through cataract. I can barely see her optic nerve through the optos. I couldn't see anything with a 90 at the slit lamp. And then look at her OCT. Look at how narrow those angles are. I mean, you can barely slip a diamond blade in here. And then you see her cataract just approaching the endothelium. And on the Pentacam, it just looked closed. It's just, what are we doing? Okay, so I used a femto, of course, right? I'm going to cheat at every chance I get, all right? So, and then I gave her preoperative laser iridotomies ×2 and tried to make sure they were very well open. I gave her mannitol in the pre-op to deturgesce her vitreous jelly. This is highly cohesive viscoelastic. It goes in the eye like packed mud. It's Helon GV. I don't have to worry about the rhexis. The laser did it for me. Thank you very much. Very gentle hydrodissection. It's already a huge lens. I don't need to make it bigger. And then very low flow, low bottle heights here. And I'm always keeping the eye inflated, though. I'm never letting it deflate because then I could get a uveal effusion because the vortex veins can be obstructed. And then I'm just slowly taking it all out, get out my last little bit of cortex. And you might watch this video and go, well, that was boring. Yes, that's the point, okay? I am on pins and needles this whole case. All right, all these patients get a CTR, all of them. Okay, they have weak zonules, they have lax zonules, this helps that. They tend toward, like I said, iritis and CME, which means that they get a little inflamed, so I polish them. Okay, nothing fancy with the lenses, but sometimes it's even hard to find a lens that's going to work for them, but a monofocal is going to work best. But trust me, you take someone from a +8 to plano, forget about multifocality. They're going to love you, okay? And then I'm making sure under viscoelastic that PI that I did is wide open, and that if I have to do an iridozonular hyaloidectomy, I can with the egg. And sometimes For really short eyes, you'll actually take the vitrector and put it right through that and eat the zonules and eat the anterior hyaloid face and take a little vitreous with it, okay? And then I'm going to stitch this wound because they can get effusions. I'm not going to put a blind vitrector in the pars plana and do a dry vitrectomy. There's too many things to hurt. The retina inserts in odd areas. You might go right through the retina trying to do that. Don't do dry vitrectomies. I've heard it advocated. It's not smart. And it causes uveal effusion as well. So now that I got my stitch pre-placed, now I go in and get all my viscoelastic out and then hydrate the wounds, keep the pressure nice and normal, and then just tie off that stitch just so that they don't rub it open or something like that. There's already too much risk here. Anytime the risk factors start going up, I throw stitches in eyes just to make me sleep better. But that's the surgery. Here's the rules. Feel free to take a picture of this. I call it the Cincinnati protocol because Mike Snyder's too modest for me to call it the Snyder protocol, okay? Number one, IV mannitol, about half an hour to 45 minutes before surgery. It's usually about 50 cc's of it. But you got to get clearance if they're fragile from their primary care doctor. But I've never had someone not get clearance for that. What Mike likes is general endotracheal anesthesia with paralytics. I don't have that in my surgery center, so I just give them a solid block, okay? So reverse Trendelenburg, their head above their feet, so you don't have a bunch of venous backflow pushing on the eye during surgery. High viscosity OVD, so that's either Helon 5, Helon GV, something like that. Somewhere it's the sodium hyaluronate, about 3.2 million Daltons is the weight you want to look for. If they have Fuchs, you can do a dispersive, and then in the soft shell technique, put the cohesive under it so it squeezes the cohesive up against the endothelium. And Fuchs is actually kind of common with these people. So as I said, do Vega without a limited dry vitrectomy. Do not blindly stick the probe in the pars plana, okay? You don't need it. The mannitol works better, and you have a risk of RD going through the pars plana because these eyes have very unusual anatomy, and you can't just measure 4 millimeters back and think you're safe. You are not. I'm a big fan of femto. Mike doesn't use it, but why not get these steps out of the way easily before I open the eye? Okay, second page here, there's only 10 points here. CTR, usually it's a type 10 because they're small, tiny eyes, but every ophthalmic eye under 20 millimeters gets a CTR automatically. And then, as I mentioned, that superior iridectomy with a vitrector, you can do it, you don't have to if your PIs are wide open, but if there's any doubt or if it's flopping back and forth in surgery, put an anterior vitrector through a PI, right through a little paracentesis right there, vertically placed paracentesis that you're going to have to stitch, put it right through the PI, into the zonules, through the hyaloid face, and make sure that if there's any fluid that wants to flow back and forth, it'll do so easily back and forth and not get trapped behind the capsule. Now, be ready to do a scleral window. If they get a uveal effusion, you've got to do a radial cut down about 5 millimeters back, use a little Kelly punch and take some bites away from those edges of the cut down, and then microcautery to those edges and evert them, okay, and then close the conge over the top with Vicryl, and that'll let the choroid effuse through that incision that is not easily closing and healing back. It's going to be an everted and burned edge, so it easily burns out there. Now, here's another challenge. Powers of lenses. You can get 40 diopter lenses. That's an SS6AT. I don't even know if they make those anymore, but Alcon typically has about a 40 diopter lens. Other carriers have 35, which usually isn't good enough. You can get CUDE is compassionate use device exemption from the FDA. So in Europe, Human Optics makes a 60, and then Solico out of Italy makes a 70, up to a 74. So if you're having to get compassionate use exemptions and you've never done this before, stop. Send it to Mike Snyder. Don't send it to me. Send it to Mike Snyder. He's in Cincinnati. These people, it's worth the plane ticket to get safe surgery versus losing their eye. They're very rare, but the 20 millimeter cases will come to you, and you can do them. Just be careful. So these eyes require special attention, special techniques. Only experienced surgeons should be doing these eyes. You know, I mean, if residents are doing it, the experienced surgeon has to be right there. As I said, special lenses, even a device exemption may be required, and patients have to be well consented at how dangerous this is. And oftentimes they come to you with really dense cataracts because no one's willing to touch them. So, questions on small eyes? I haven't found it yet. Because some kids are coming at 10, and you still fit them in when they were 10. So, yeah, I've never seen anything less than 10. I mean, then you're kind of getting to like microcornea, and that's a completely different story. Yeah. I mean, then it will just go in a scleral tunnel anyway. So.
Do you have an accidentally cut off or refractive
So the people who come to you are going to be +8 and they're miserable, right? So as long as they're properly consented, no. But I guess, I mean, how miserable would it be to have a 16 millimeter eye, right? Like, it's dangerous surgery. But if they're non-functional and they understand the risk-benefit alternative and you go over everything, and if you do it right, like I told you, it actually becomes a manageable surgery. All right, on to the next one. All right, keratoconus. All these people are wandering around the world trying to find someone who did LASIK on them. Right? That's like their life's mission is to find someone foolish enough to LASIK their keratoconus, okay? Because they suffer. You know, the glasses don't work. The contacts are irritating, especially in Arizona. You know, it's dry, it's dusty, right? I have no financial interest in anything I'm going to talk about here other than the fact that I'm a surgeon. I get paid to do surgery, but the companies that are associated, I don't have any interest in. So here's a 48-year male who came to me, and he had keratoconus, and he's just becoming non-functional with the sclerals. He can't wear them. They're uncomfortable. They fog up. So he's intolerant of his RGPs now. He's never been cross-linked. He doesn't rub his eyes. But that's his left eye, 73 diopter cone. He's a -27 +10. And here's his right eye. He's a -12 +14. So he can't fix it with glasses, can't wear his contacts. Now he can't work, and now he doesn't have insurance. And I'm just comping him the visit. I'm comping him the Penacam. One of my ODs refers to me a lot, like, this is a super nice guy. You just see him. I'm like, sure, I'll just bring him at the end of the day, and I'll just see him. We won't charge him a dime. What are we going to do for him? I'll tell you what I did for him. I made him a -1/4 +75 by 150, 20/30 uncorrected. Magic. So this is the Penacam showing the progression. And so what you want to pay attention to is the difference map, is the one on the far right that's all purple. He's got 20 diopters to 22 diopters of flattening of his cone. And what we did, if you look real close here, let's see if I can show you. You see right there? See that? That is a semicircular corneal graft that was irradiated to kill the cells and fixed. And it was very custom made for him based on the size and shape of his cornea's cone. And then a femtosecond laser made a tunnel, like an Intex tunnel, and I slid that piece of cornea in there. And based on very complicated nomograms, we knew that if we put 500 or 400 or 300 microns of cornea of a certain arc length and a certain diameter and tucked it into a tunnel in the cornea, we can flatten his central cornea. And it's pretty darn close. So that is called CTAC, for corneal tissue addition keratoplasty. And it's kind of a logical extension from initially Intacs, and then what Susan Jacobs developed in India, which is CARES, and then more of, hey, let's not throw away cornea tissue from DMEC prep or things like that. Let's actually use that tissue to thicken up and bolster what's going on in a keratoconic eye. So the original idea, we talked about this back in 2012, 2014, when they started to do SMILE studies. Like, wait a minute, when you do SMILE and you cut out the lenticule to fix their myopia, couldn't we insert that lenticule into someone else and fix their keratoconus? And we did that. Hirsch did that. But when you implanted the tissue in the visual axis, it got hazy. So he said, well, let's just cut it out of the visual axis. Let's just do an arc. And from 2016 till now, 10 years, they've been doing this, and they've been building the nomograms. Okay, well, if it looks like this, how much arc length, how much thickness, how much depth? And now it's all spelled out for us so that we can do CTAC, and this is basically, it's salvage surgery for keratoconus, but it's refractive surgery for keratoconus. So it's a customized allographic tissue. It's expertly designed, each patient individually by Hirsch and Greenberg. And you have to have a special femto to cut the tissue both at CorneaGen in Seattle and then also in our ASC. And it flattens the cornea greatly, reduces their refractive error, and thickens the thin areas. And so you can see here that this is exactly how we design it. Like, we're looking at the aberration map and the curvature map, and then we figure out how many millimeters from the center of the pupil that will be to kind of avoid getting into the visual axis, and how wide is it, and how many arc degrees is it, and how thick is it, and we figure it out. So, there obviously are ideal candidates. Mild or moderate is far better. No scarring the visual axis, at least 300 microns of cornea. You get above 70 diopters in your cone, it's not as effective. So you don't want to wait till they're as bad as they can get. So within 6 millimeters of the visual axis is where we want the cone to be. If you start pushing it out to the 6 to 8, it's possible. When you get out to 8 millimeters or more, this keratoconus is really kind of shifting along to maybe more of a pellucid pattern, and it doesn't work very well. So ideally a 6, acceptable 6 to 8 in terms of where the cone is positioned, and 8 millimeters out from the center, not going to do it. So here's some ideal candidates with their cones either central, or they kind of have a crab claw that's more or less central, but within that 8 millimeter zone. And then when we start seeing this, we're like, oh, we could try it. We don't know how well it's going to work. And then when we see this, we say, no, we're not going to do CTAC on those cases. So it's not for everybody, but for a large number of keratoconus patients, it does work. Okay? There's the cone in the center of the pupil, and we look at that thinnest point, make sure it's thick enough, 300 microns. So this is just a Pentacam. I'll just go through these quickly. But here you can see before surgery, the central cone. After surgery, quite flattened, and then the difference map, very blue, that this particular case was 10 to 12 diopters of flattening. Fantastic. And these people go from, functionally blind to 20/30, 20/40 uncorrected. So they love you. I won't spend too much time on this. Just tell you have to have the special tomographer, either a Pentacam or a Zemer. You have to have one of these lasers, and then there's some special instruments for surgery that we need. Can you do cross-linking? Yes. Should it be before or after? We don't know. Okay. I kind of think it's after. Other people try it before. It doesn't seem to make a huge difference. You don't care about the instruments per se, but that's where you get them. And this is just for people who are actually training in CTAC, okay, and how to transfer the scans and how to fill out the paperwork and things like that. It costs about $19.50 from CorneaGen, so that's cheaper than a cornea transplant because they're getting several segments out of a corneal transplant, and insurance pays for it as an anterior lamellar keratoplasty. So fantastic. So CTAC, cool stuff. Questions on that? No, not even close. As a matter of fact, people with intacs come to me and I take them out. All intacs erode eventually, and they get 1 or 2 diopters of flattening with intacs, and the cornea hates to have foreign objects placed in it. So I don't do intacs, I take them out. I've seen too many of them erode and get infected. But that was the initial idea that led to this logical conclusion, was starting with intacs back in around 2000. Where are we at with time? 10 minutes, cool. All right, we're going to finish up on cool cases. What would you do if somebody went and had a vitrectomy for a dislocated lens, and the vitrector get a snake bite right there and ate up the iris pupil sphincter? Whoops. Well, it's pretty simple. And by the way, you can see the little blue dot sitting out there. That's the Yamane bulb, okay? But here, we just come in under some visco, and we just bring together the 2 edges of the iris sphincter. And I'm sorry, I'm usually not that unsteady. The video's sped up a little bit. But you just put a stitch across it, okay? And then you reach in there with a little hook. This is a Condon snare. Gary Condon from Pittsburgh developed this for MSD. And I pull out a loop, and then I do a Seepster sliding knot or a 4-throw pupiloplasty pass, and then I pull it together. And it's, how do I know that it's going to be right? Because I've done a lot of these. So the first few you do, you're like, oh, I'm off. Okay, cut it out and do it again. But don't cheese wire the iris too much. Okay? These people love you. I'm just cutting my other Intar scissors was broken, so I had to use the bigger one. But everything's done through 2 or 3 paracenteses here. So you get a little bleeding. That's fine, and it happens because you're just tugging at the iris space there, and it bleeds a little bit. Here, my last pass, I'm shooting a little different method. I'm putting the needle in there, and then I have a cannula. And I just ride up into the cannula and then pull that through so that it doesn't get caught on the paracentesis on exit. And then hook it, tie it, cut it off, and clean up all the blood and visco. And they look like this, and they're very happy. Now, it's oblong because they're still dilated partially in that other area, but it'll come back to normal. And so they're pretty happy. They do really well. So that's pretty simple. And we do iris repairs all the time for little nicks on the iris. But this patient, they had a little bit of rough cataract surgery, and there's just a big chunk of iris missing here that's kind of by scar tissue. And I have the vitrector in there, and I'm sculpting away the scar tissue because they're actually scarred to the capsule and the lens. And another surgeon already tried to repair it, and it just didn't work. Everything just cheese-wired through. So you can actually see the processes of the ciliary body there on the far edge. And so I'm just trimming all the scar tissue away to free things up. And when I'm done with this, the gap's just too big. You just can't sew it together, okay? So what I'm gonna do with that is 4 months earlier, I had taken pictures of their eye, and I'd sent off those pictures to Germany, and they'd made me a custom iris prosthesis. And now these are FDA approved, and they're only $10,000. It's a really good deal. And so here's a little intraocular measuring stick, right? And it showed me how big I need the iris. And then I took that, and then this is by Mateen at Epsilon. He made this for us, where we put the iris in the middle, and then that just pulls it to center the trephination on the outside to the pupil on the inside. And we push the trephine through and get the pupil properly centered. And then we load it into an emerald injector, which is the Johnson & Johnson old-style injector with a lot of viscoelastic. Then this iris was custom made to match the iris pigment pattern of this patient. Now, it doesn't look the same in the eye under the surgical microscope as it does in real life. In real life, these are amazing matches. You just can't believe how good they match. But when you look at it on the microscope, because of the lighting of the microscope and the different reflective characteristics of the iris versus the iris prosthesis, it looks different. But you can't tell. If you met this person, you would not be able to tell. So I'm just making sure that this thing went into the sulcus and that it's gently placed and that it's not pinning any iris or any remnant of the iris. And it centers well, and it also is not floating back and forth, or it's not bowing up. So it's not under tension on the ciliary body, but it's not going to bang into the ciliary body floating around. It's a Goldilocks. It's just right. That's why I measured twice and cut once. And so fixed her glare beautifully. She's super happy. Stitched there always, and looks great. So she's naming kids after me. And then the last case, this lady was born aniridic. And so she comes to me in her 70s, and I did her cataract surgery, and I put an LAL in each eye, and I fully adjusted the LAL, and we did a YAG. And then we waited for about 3 months, made sure nothing changed. And she got to choose whatever she wanted, because she's got a little bit of brown stump there of iris, but not much. She goes, I want kind of hazel greenish eyes. I think that'd be cool. All right, so there I'm doing my measuring stick. Turns out in this case, I'm 12 to 13 sulcus size. It's a 12/8 on the devices that come, so I don't have to trephine the device. And I always measure from 2 different angles to make sure it's correct. And then we load the the iris, and then we put it in the eye. And now I've messed up in the load a little bit. See how the black part, the backside, is kind of folded up? It should be folded down, but that's okay. She doesn't have any other iris to mess with, so I think it's going to work fine. But this lady was so happy. I did this for both eyes, and then she's sending me pictures from her taking Viking cruises in Germany and sitting in the sunroom and visiting all these places in Europe. And she's like, I wanted to do this my whole life, and I couldn't do it. I had to stay inside because it was just terrible. The glare for 60-some years of my life was terrible. And now when you look at her, you can't tell that's an iris prosthesis. It looks perfect and beautiful, and she's thrilled. So pretty cool surgery. Now, is it technically hard to do this surgery? No. But should anyone do it? No. These eyes are messed up. Okay, aniridic eyes have a lot of problems like anterior fibrosis syndrome and weak zonules and all this other stuff, and post-traumatic eyes. So it's not the iris that's hard to do. It's the eyes that need it, have been through the ringer, and you have to have a lot of experience to do these. So there's not that many people doing them, but it's FDA approved, it's beautiful, it works so great. And so if you see people with intractable glare or iris problems, send them off to me or Mike Snyder, or UCLA does them. So there's a couple people out there doing them.
Does that eventually cause any issues in the intractable meshwork, pressure issues later on?
No, haven't seen any problems, and we've been studying it. I was part of the studies since like 2009, so it's spent 10 years in compassionate use device exemptions or in studies, and so we were doing it even way back then, and it's been in Europe for at least that long. We don't tend to have problems. Commercial doesn't pay for it, even though it was FDA approved back in 2018. They still call it experimental. I'm now advising patients to start a class action lawsuit because I'm so tired of it. It's a lie. It's disgusting what insurance does these days. Medicare pays for it. And then for Medicare Advantage patients, I say, see, Medicare Advantage is cheating you because you're supposed to get everything Medicare does, but here they're denying it. So hire a lawyer and sue them. And I'm not a litigious person, but after 10 years of, or almost 8 years now, of this being FDA approved, and these people being like, you know, for these super rare people, that, yeah, it costs a lot, but they're really rare, and then we're not going to pay for it anyway. I want them on the front page of the news. I want everyone to know what evil people run insurance companies and how they'll screw these people. So I've taken off the gloves for them because commercial payers won't pay for it. So it's $10,000 just to have the device made before you even show up to surgery, and then another couple $1,000s to have surgery. It's, you know, the Medicare reimbursement for the surgeon here is around $15,000. Other questions? Yeah. Oh, that's I think it's a 3 or 3 1/4. Yeah. They kind of choose the the best medium. All right, you guys have been great. I think we're 3 minutes ahead of schedule. Nice.
Okay, everybody, I think that concludes our instructional courses for the conference. Thanks, everybody, for coming and staying till the very end. I just want to express my gratitude to the subcommittee chairs, Austin Taylor, Maya Kahara, Frank Lee, Scott Peterson, Victoria Williams, Will Sawyer, and Tim Winter. Thank you, guys. You've done a lot for this conference, getting us great speakers. And Dr. Elias Koren and Dr. Morrison have helped Education Committee as well quite a bit. So thank you all. Please, a couple housekeeping things. You will be getting an email with a CME certification, so make sure you claim those. And there will be a survey at the end that will help us tremendously in organizing next year's meeting. So any suggestion, recommendation, applause definitely help. So thank you. Drop your lanyards at the checkout, and unfortunately there is no lunch today, so everybody's on their own. There is a strabismus lab at 1:30, so everybody's welcome to that. Thank you. Thank you. That was awesome. You are just all the amazing things. It's kind of crazy.
You gotta do fun.